This video will take a look at various properties of waves, just very general waves that apply to all types of situations we'll look at. We'll look at some specific characteristics like amplitude, wavelength, frequency, and wave speed, as well as look at the difference between longitudinal and transverse waves. So first of all, let's look at the start of the wave. There needs to be a source that controls how the wave is being created. And that source, for say a slinky wave is somebody's hand. Or for a sound wave, it is the vibration of something. But whatever that source is, that determines the frequency of the waves, or the rate at which the waves are produced. Frequency is measured in hertz. Hertz, abbreviated Hz, and a hertz is 1 per second. So when we talk about frequency, we're talking about how many waves are being produced per second. The period is the exact reverse of that, but the two ideas really describe the same concept, how often waves are being produced. Period just measures the time between each wave's production. And so the period is the reciprocal of the frequency. Therefore, the standard units for period are going to be seconds. The wave source also controls the amplitude of the motion. The amplitude refers to the height of the wave. If it's a spring or a slinky wave, what's called a transverse wave, then the amplitude is measured from the center point, what's called the equilibrium line, to either the crest or the trough, one of the high peaks or one of the low peaks. It also has a connection with the type of wave. An amplitude is going to mean something different for a sound wave. It'll be an intensity or a pressure versus a light wave, which there the intensity refers to the brightness of that light. And so it has to do with energy and again the sort of the power of that wave. It's important to recognize that in our formulas you won't see amplitude written because amplitude does not affect the other properties of the wave. You can have a very soft sound or a very loud sound that is that sounds the same in terms of its pitch. It all comes back though to the source of the waves has to do with something that vibrates. Always sort of keep that in mind. Again, the source controls the frequency and the amplitude. If you create a wave that has a low amplitude, that again is going to be associated with energy, a low amount of energy, and a high energy wave is going to have a high amplitude. And that's regardless of whether it's a sound wave, a light wave, or an ocean wave. Now the medium or the material that the wave moves through determines how fast the wave moves through or propagates through space. And so that is determined entirely on the material. You cannot control as the source what the speed of the waves is. You can control how often waves are created, but the actual movement of the wave through the material is determined by the material itself, the medium. And you can measure the speed simply the way we've always measured speed, as a distance over a time. The unit is meters per second. You can just sort of watch one point on the wave as it goes across, as it goes past you, and time it just like as if it were somebody running. You can sort of see that in this picture here. If you watch like a peak, okay, you can sort of see how that peak moves across the screen. You could time that point moving across the screen and how far it actually traveled. That would be the wave speed, where the frequency has to do with this part over here, this red box, where the waves are being produced. So here, if we measure the time to go from, let's say here, up and back down again, That time would be the period, and however many times it did that within a certain frame of time, that would measure our frequency. So frequency has to do with the source, wave speed has to do with the motion of the waves through space. If you put these two ideas together, you're able to determine the wavelength of the wave. So if we have a consistent medium and we put in a wave that has a high frequency where the waves are being produced at a high rate, they're going to be squished together. Okay, there's not going to be a lot of space between the different points, and the wavelength is going to be small. Okay, whereas if the frequency is slower, okay, a slower rate at which waves are being produced, then they're going to be more spread out. And we call this distance from peak to peak the wavelength. We'll get to that a little bit more in a second, but the wavelength describes how the actual distance in meters between identical points of a wave. When you put this together, that wavelength then, it's going to be increased if the speed is faster, and it's going to be decreased if the frequency is higher. And so it's proportional to the wave speed v, and it's inversely proportional to f. We use the symbol lambda, a Greek letter, for that wavelength. It's kind of a wavy L. L is the Greek letter L in the letter L in the Greek language is called lambda. And so that relationship, it can be written like this, but more commonly it's written like this, and it's called the wave equation. You should make sure that you write that down. So there's really two basic types of waves that we talk about. You can also have a combination of the two of them. One is called a transverse wave, and this is where the material moves perpendicular to the actual propagation of the wave. So if you look at this wave that's going back, if you look at the whole system, you should be able to see that the flow is to the right. The wave is moving to the right. But if you look at just an individual dot, it's just moving up and down perpendicular to that motion. So the wave is moving this way, but the particles of the medium move up and down. The particles themselves never move with the wave. It is just the energy of the wave that propagates or moves through space. A longitudinal wave has the motion of particles going back and forth. So if you watch, there's a red dot here. If you watch that red dot, you can see how it's just moving side to side. And in fact, all of these dots, if you just watch one dot, you can see that it just moves left and right at a regular rate. The rate at which that dot oscillates, that's the frequency. But it definitely, you can see this progression. It looks like there's almost like a cluster of dots going across. It's not. They are just moving back and forth. But it appears as though the wave moves to the right. That would be the wave speed if we measured how fast this like section is moving. But the frequency would be how quickly an individual dot moves back and forth. This is called a longitudinal wave, where the particle's motion is in the same direction as the actual wave's motion. In summary, again, you may want to jot some of this information down. Longitudinal waves, the material moves back and forth along the same line as the actual wave's propagation. Good example are sound waves or pressure waves. Transverse waves, the particles move up and down perpendicular to the motion of the waves themselves. We tend to draw transverse waves and think about them more often, just simply because they are easier to visualize. If we did want to visualize what the wavelength of a longitudinal wave would be, it would be something like this. You'd find a section of high compression, and then the next section of high compression, and the distance between them would be the wavelength. Whereas with a transverse wave, it's best to just pick a high point to a high point or a low point to a low point. And that's a great measurement of the wavelength.